Welcome to Lesson 2 of Module 3 on Designing Fair Models and Data Integrity and Analysis. Today, we will cover using Human-Centered Design, HCD, to formulate fair models. We will also discuss data integrity and documentation. We will end with exploratory data analysis and quantifying bias. Let's begin with designing fair models. To help with the design of fair models, it is important to consider how the AI system will impact humans. Human-centered design, HCD, is an approach that aims to make AI systems relevant to the users by asking questions to clarify their needs and requirements. HCD also considers the risks AI can pose. Human-centered design is a big area of research. The main goal of HCD for AI is to ask questions about potential harms and risk, as well as the value proposition of using AI. From a practical design point, you should verify that safety measures are in place for AI systems. You should also include mechanisms to allow end users to challenge unexpected model behavior and outcomes. Now, we'll move on to data integrity. Bias in the outputs of ML models can stem from bias in the training data that algorithms learn from. Bias in the training data can be because of biased sampling. Therefore, sampling methods that systematically overrepresent or underrepresent certain groups should be avoided. Some types of bias from bias sampling include selection bias when samples are from a different distribution, measurement bias when different measuring devices or techniques are used, and confirmation bias when outliers are wrongly discarded to match existing beliefs. There also may be quality issues with features and labels. Therefore, avoid using data that perpetuates existing biases, and avoid indirect measurements. An example of bias that emerges from this is historical bias, when outdated, known to be biased samples from society are used. Better data integrity may reduce bias in the data. To help achieve data integrity, address these two factors. For data quality, select meaningful, high-quality features. For data sampling, use valid, fair sampling and storage techniques. Check for consent and avoid data duplication. High-quality data tends to be robust and objective. Data should meet these criteria. It is quantifiable, meaning features are true measurements of certain characteristics. For example, the number of messages between peers should be used, as it is a direct measurement rather than a connectedness score, which is subjective. Data should be able to be measured directly, so features should not be outputs of another model or compounds of different features. And it should be understandable, with the feature names being easy to comprehend. For instance, monthly bonus, rather than MB. Biased datasets in NLP and computer vision are a significant concern. Historical and societal biases are often present in data collected from the wild, meaning real-world sources. For example, research has shown that word embeddings, which are vector representations of words used in natural language processing, can encode societal stereotypes. This can lead to biased and discriminatory outputs from language models trained on such data. In the field of computer vision, many widely used datasets suffer from a lack of geographical representation. ImageNet, a popular dataset used to train neural networks for image classification, contains more than 15 million labeled images. However, these images come from only a few nations, leading to potential biases and limitations in the performance of models trained on this data when applied to images from other regions or cultures. Challenges to label quality are important to consider. Tainted labels generally describe what happened historically, but don't tell you what the unbiased outcome would have been. To mitigate bias, you need to address the underlying causes of inequality using bias transforming metrics. Labels can be insufficiently precise to capture meaningful differences between cases. To mitigate bias, collect additional information or clean labels before passing them to a machine learning model. A datasheet tries to capture all the important information about a dataset that is used to train a model. To complete a datasheet, you must answer several important questions, many of which can help to identify bias before the model is even trained. You may find the following information in a datasheet: who collected the data, what purpose it was collected for, when, where, and how it was collected, and descriptive statistics of the dataset. Let's talk about exploratory data analysis for identifying bias in data. Recall that exploratory data analysis, or ADA, is an approach to analyze a dataset and capture its main characteristics. ADA can help you find correlations, missing data, and skewed distributions. ADA techniques are used to identify bias in the data. In general ML, ADA helps to discover patterns, spot anomalies, test hypotheses, and check assumptions. In responsible ML, ADA can help identify collection gaps, inform further feature processing, and detect societal and historical bias. As part of ADA, you can analyze the distribution of the labels to detect an imbalance. Samples per class might not be equally distributed, and the ML model might not work well for the infrequent labels. In the chart on the slide, more data points are available for the denied label than for approved. Models learn from data, so by seeing more negative outcomes, the model might predict more negative outcomes in general. The high accuracy paradox is that if a model works well for the majority class, it is considered accurate. But this can be especially bad if one group of people is overrepresented in a certain outcome class. Group imbalance can pose an additional complication, especially when negative outcomes are disproportionately concentrated in one group. Therefore, you should visualize and quantify labels per group. Also, beware of bias sampling by checking for minority groups in the dataset. There are general ML measures to quantify label imbalance, and also responsible ML measures for quantifying imbalances per subpopulation. Class imbalance, CI, works to assess the imbalance in group sizes. Positive class imbalance values indicate that Group A has more training samples in the dataset, and a value of 1 indicates that the data only contains members of Group A. Values of CI that are near 0 indicate a more equal distribution of members between groups. A value of 0 indicates a perfectly equal partition between groups and represents a balanced distribution of samples in the training data. Negative C values indicate that Group B has more training samples in the dataset, and a value of -1 indicates that the data only contains members of Group B. Difference in proportion of labels, DPL, is specifically used to assess label distribution. Another metric is difference in predicted proportion of labels, DPPL. The equation is the same as for DPL, but the numbers come from model predictions rather than training data. You can often observe a shift for the worse in predicted labels. Positive DPL values indicate that Group A has a higher proportion of positive outcomes when compared with Group B. Values of DPL that are near 0 indicate a more equal proportion of positive outcomes between groups. A value of 0 indicates perfect demographic parity. Negative DPL values indicate that Group B has a higher proportion of positive outcomes when compared with Group A. Why do we need bias metrics? Normalized class imbalance helps detect whether there's enough data for each subpopulation. The outcome might suggest that you need to obtain more data. Difference in proportions of labels allows you to detect bias in the dataset. You can measure pre-training demographic parity as the baseline. Many more pre-training metrics exist to evaluate potential biases and imbalances in datasets. This slide provides an example of calculating CI and DPL metrics on a sample dataset. Note that the groups are represented almost equally for denied outcomes. However, Group B makes up a small portion of the total number of approvals. For information about additional metrics to measure bias, see Measure Pre-Training Bias in the Amazon SageMaker Developer Guide. In the next lesson, we will talk about fairness criteria, which are mathematical ways to describe fairness in ML models. Thank you for watching.